Okay, hello everyone. Welcome to Chem 6374, Physical Inorganic Chemistry 1. Sorry I'm not able to be there for the first class, but hopefully this recorded lecture will help us stay on track and not get behind at the beginning of the semester. So what we're going to do today, and really on Thursday as well for the full first week of class, is kind of go over some review topics, some things that ideally you should have learned as an undergraduate student, either in general chemistry or inorganic chemistry. If you've forgotten any of these things, it's good to try to review some of them at the beginning of the semester to make sure that you're all caught up as we get into the more in-depth material. This course does not require a lot of prior chemistry knowledge, but obviously as a graduate level chemistry course, I'm going to expect that you have some things pretty well handled from your undergraduate and not have to teach everything from the very beginning. So what we're going to do today is first start by going over the syllabus a little bit. The syllabus is posted in Blackboard. I'll get into some more details about Blackboard in a second, but you are able to download it and read it in full detail if you'd like, but the material that I have in these slides should cover just about all of it. Alright, so what we want to mention again is prerequisites for this course. If you're a UH student, you may have taken Chem 4365, which is the second semester undergraduate inorganic course. Basically, as long as you've taken the undergraduate inorganic chemistry sequence, you should be ready to go for this course. So if you're worried about your preparation for the course or what prerequisites you have, we can talk about that, but I've never really had a student that seemed to be totally unprepared for this, so you should be all set. Alright, so we have a recommended textbook called Molecular Symmetry and Group Theory. It's a pretty small paperback book, so it's nothing that's going to be too heavy to carry around or anything. You can buy this at the UH bookstore if you'd like. I have copies on order there. You may be able to get a better price though online from something like Amazon or other online book dealers. It's not a terribly expensive book as far as I know, and I would also mention that it's not absolutely required. But it is recommended. So I aim to make the notes that we have in this course fully inclusive, and if you're showing up to class and taking the notes and looking at them as I post them, you should have enough material to succeed. But it is sometimes good to read about some of these things in more detail, and I do think this book is written at a very good level to be able to understand it well and to really be a useful resource for you for most of the topics that we cover. There are some things that we'll do that are not at all dealt with in this book, but this is a pretty good introduction to most of the things that we do. So I do recommend the textbook Molecular Symmetry and Group Theory by Carter. So Carter's the author's name, and that's the one that we'll be following more closely. There are some other books listed in the syllabus that you might find helpful, ones that you may already have or you might be able to find at the library. For example, Al Cotton's Symmetry and Group Theory book is another very good one, but written at a slightly higher level, so I think the Carter book is a better introductory source. One thing you're certainly wondering about in this course is the grading scale. So there are really two ways that we determine your grade. So we have homework assignments that'll be approximately every other week. That's going to be 10% of your grade. I welcome you to work collaboratively on these. I don't mind if you work together. But really the point of the homework assignments is for you to learn how to do the types of problems that you're going to see on the exams. So you're certainly going to want to put some individual effort into it, even if you are sort of collaborating and trying to help each other. And the other thing too is to realize that even though it is 10% of your grade, the points are not the important thing. What you really want from the homework assignment is to get something out of it and to use it as a learning tool. So don't stress out too much about your homework grades. I tend to grade them pretty leniently anyway. I'm strict with the grading, so I want you to learn how to what mistakes you're making, but at the same time most people have pretty good homework scores and it's not going to affect your grade too much. Now we have 3 total examinations in this course. So 2 are going to be during the semester, so during class time. There'll be 2 of those that are going to be worth 25% each for a total of half of your grade. And then our final exam, which is comprehensive, is going to be 40%. And I have some more information on exams later on, a little bit more detail about the dates and some other things. So you'll have those things added together will give you the 100% that your grade is out of, and then the grading scale is listed here. Now this scale I sort of set this based on how students did the first time I taught the course, and it's worked well for both semesters that I've taught this. This is now my third time doing Physical Inorganic 1. And here's what we have. If you want to get an A, you need to get 85 or above, A minus 78 to 84, B plus 71 to 77, and so on. Now I should mention that because this is a graduate level course and because the sample sizes are pretty small, there's going to be some variation from semester to semester in how the students do. So I do reserve the right to change the grading scale, but it will not be made more difficult. So in other words, if you get an 85%, you are guaranteed to get an A. But I may make it a little bit easier to get an A if I feel like that's necessary. But don't count on the grades being curved anymore beyond what I have here. My strong preference is to just use the grading scale that I've listed here, not have to change it at all, and hopefully that will work out for us and give us the grade distribution that's reasonable for a graduate level course. I should point out that you'll have to work for your grade, obviously, but I've had very few students get below B's. As you can see, you only need to get a 62 to get a B, so it's not a terribly difficult scale, and grading should not be something that I think is a very big deal for us in a graduate level course. We're here to learn, and the grading is sort of something that will not, that'll take care of itself and not have to worry about. Alright, so I do want to talk a little bit about this system called Blackboard that we're using. If any of you did your undergraduate studies in the United States, you probably already know what Blackboard is because everybody uses it. But if you're from another country, this might be a new concept. So Blackboard is just a course website that we'll use to distribute documents and post some announcements and things. So you can access this through Access UH. And so everything that we need for the course is going to be there. So the syllabus is there. And then for the lectures, as you'll already see if you log in, for this one today, before the class starts, I'll post blank lecture notes. So those are notes that are kind of an outline format, or skeleton notes, if you will. And you're welcome to print those out and bring them to class. Many students find that helpful. And then after each lecture, I'll post the completed lecture notes. So you'll have full access to all the lecture notes through Blackboard. They'll just be available for download as PDF. And then all the homework assignments that I give out will be posted on Blackboard. I'd prefer not to have to bring hard copies all the time. I'll just post them there, and you can print them or just do them on your own paper, however you prefer. But the homework assignments will be there. I will post homework answer keys so that when you get the homework assignments back and they're graded, you can know why you missed certain questions, why you lost certain points, and see really how to do the problems. And then for the exams, I will also post the keys after they're finished, of course. Alright, so in other words, all the important documents for this course will be available for download on Blackboard. AccessUH.edu is where you'll go to find Blackboard. I have a screenshot on the next slide that sort of shows you what it looks like, or you can go directly to the Blackboard site and log in there. And you're going to use your regular UH login credentials to get in. One thing to be aware of is that the easiest way for me to send emails to all of you at once, if I have to do that, is using the Blackboard system. Those emails by default will go to your uh.edu email address, so make sure you know where that email is going, make sure you're checking it. It might be possible in your Blackboard settings to change the email address that your Blackboard announcements go to, but I'm not really sure about how that looks in the student view. But anyway, make sure you're checking your UH email, because that's likely where the course announcements are going to go to. And so anytime I have anything to tell you guys via email, you want to make sure that you don't miss it. Here's a couple of screenshots of what Blackboard looks like. Alright, so again, if you go to Access UH, that's one of the most common ways to log into Blackboard. It'll look, your page will look something like this. You might have different icons because students don't have all the same programs and services available in that. But anyway, you should see a Blackboard Learn icon somewhere. Mine's right at the top of my list right there. And so that's one way to get into Blackboard, but like I said, you can also directly access it and log in. Once you log in, you'll find our course, Chem 6374. It's possible that other courses you're taking will use Blackboard as well, so you'll have a few courses to choose from. Anyway, once you get into my course, the homepage sort of looks like this. I have some important information to read here about lectures and exams and homeworks and things. And then all of this stuff down here is the course content that I referred to. So lecture notes, the periodic table and the character table, stuff that we'll use especially later on, Tanabe-Sugano diagrams, which again we won't use until the end of the course, but they're there already if you want to look at them. And then I'll start adding some more things here as well as the semester goes on. We have homework assignments and exam keys and all that. So there's going to be different folders, different files that you can access here, and that's where all the course content is. It's also possible to check your grades in Blackboard, although our grading system is fairly simple, so it shouldn't really be something you'll have to update all the time, but I think there is a grade book in your view that you can get to. I'm not sure if it's showing up here because there are no grades yet, but once I start putting grades in, you'll be able to access those. But again, there's only a few grades you have to keep track of. All right, and then finally, some last bit of important info from the syllabus and things related to this course. If you do ever need to talk to me about the course, whether you have questions about the material, you don't understand something, you just want to sort of discuss your progress and how you're doing from a grade standpoint, you're always welcome to come talk to me. Some of you have found my office already, but if not, it's in Circ 5023. That's sort of right next door to the SEC building, which is where we're supposed to have class. Again, that might change, but assuming we're having class in this building, my office is over here right next to it. You should all know where Circ is, especially if you're a chemistry graduate student. It's one of the main chemistry buildings. I'm not going to have set office hours for this course. There aren't really a lot of you, so and also you're all going to have different TA schedules and things. It's going to be hard to find a time that works for everybody. So for office hours, you can come basically whenever you want. You can walk in. If I'm in my office, I'd be happy to talk to you. There's no guarantee I'll be here all the time. Occasionally I'll travel. Occasionally I'm doing other things on campus. So if you want to make sure that I'm going to be around, you can always email me ahead of time and schedule an appointment. And as long as I'm available at that particular time, I'd be happy to meet with you. So I'm going to try to keep the office hours flexible so that you can work it into your schedule as much as you need to. And that worked well last semester for this course. I didn't have to worry about scheduling certain hours, and you didn't have to worry about whether you had conflicts or anything. Email is usually the best way to get a hold of me. So tteats@uh.edu is my work email address, and again, that's the way that you're going to want to contact me. And my office phone number, if I'm in my office, I'll certainly answer it, is given here as well. In terms of some other things, exam reviews, we may have some group exam review sessions before each examination. I think last year I just did extended office hours, and that worked fine, where people would just come and ask me individual questions. But if we think it's something that we're interested in, I could set up exam review sessions, provided we're able to get a room to do that, maybe just one of the conference rooms. The exam dates are listed on the syllabus, but I'll also give them to you here. The two in-class examinations are going to be September 28th, so about a little over a month into the course, and then November 2nd. So pretty much evenly spaced throughout the semester is what I tried to do. So September 20th, November 2nd, both Thursdays, both in class. And then the final exam is going to be December 7th. That's at least how the university has it scheduled now. They always warn us that they could change the schedule, but they haven't so far. But December 7th, which I think is also, I forget what day of the week that is, but it's one of the earlier final exam dates, and it's going to be at 11 a.m. So the in-class exams are going to be 75 minutes, so basically the whole class period. And then the final exam, I'll give you the full 3 hours to do it, although I don't anticipate it will take most of you that long. Okay, so those are sort of the details about exams. If you have any questions about any of this stuff, please feel free to send me an email or catch me when I get back on Wednesday, the 23rd, which is when I'll be back, and I should be around for most of the time after that. So what we're going to get into now is start reviewing some of the topics that we need to know to help us in this course. So a big part of this course deals with symmetry, and so if we're going to understand molecular symmetry, we need to first understand molecular structure. So we're going to go through some things. We're going to focus mostly on transition metal compounds in this class, but it also is helpful to have some idea about the structure and the bonding in main group systems as well, some things that we should have learned in general chemistry, and some structural aspects of those that will be important when we start addressing molecular symmetry early on in this course. So if we're going to determine the structure of a molecular compound, we first need what's called a Lewis structure. This is where we show the arrangement of the bonding and non-bonding electrons, and this helps us then predict the three-dimensional structure. So I'm going to give a quick review of how to determine Lewis structures. This should be pretty second nature for us, but if it's something you need to go over, please do that early in the semester to get used to this. So what we're going to first do is count the total number of valence electrons. And we're going to use the periodic table to help us do that. The periodic table in the group number is going to give us the valence electrons and so on. We'll go through some examples later on. So the group number on the periodic table is what gives us that total number of valence electrons. Remember, the precise definition are any electron that's in the outermost shell. So if it's a main group element, it's going to be the S and P electrons. And then we're going to add or subtract additional valence electrons if what we're determining has a net charge. If we're dealing with a polyatomic ion instead of a neutral molecule, we have to make sure that we account for any net charges, either positive or negative. Okay, so that's the first step. If you don't have the correct number of valence electrons, it's pretty much impossible to draw the correct Lewis structure. Then we're going to start by drawing single bonds. Now you may have learned some shortcut methods for some of these steps, so I'm giving you 5 full steps. This is how I teach the general chemistry students how to do it, but you're certainly welcome to take shortcuts out as long as they're valid shortcuts, and you've probably all done this many times before, so if you have a method that you prefer better than this, please follow that. Alright, so anyway, we're going to put the least electronegative atom in the center, and we're going to draw single bonds between all the atoms. Alright, so that's the first step, is to arrange them properly. And they're going to have at least one bond between them, of course, to hold them together. From there, what we're going to do is complete the octet. So most p block elements want to have 8 electrons around them, 8 total valence electrons. And we're going to start by doing that for the outer atoms by adding lone pairs. Alright, and those outer atoms are the more electronegative, so they get the electrons first, if you want to think about it that way. And then finally, we're going to, any remaining electrons that we have, so we started out by finding the total number, we've used up a bunch of them by completing the octets of the outer atoms. If there are any left over, we're going to put those onto the central atom as lone pairs. And as we'll see in a second, it's especially important for determining three-dimensional structure that you have the correct number of lone pairs on the central atom. So we're going to add those lone pairs to the central atom if we have any left over. And then finally, if we're trying to draw the best Lewis structure, one that is more accurately depicts bonding and things, we do need to possibly add double or triple bonds. If we have some incomplete octets, we can use those. We can use multiple bonds to address that. Or if we have formal charges, but this is not a terribly important part for this course, because what we really want to get at is the structure of the molecule, the three-dimensional structure. And this last step here really has very little bearing on the three-dimensional structure. So if our central atom does not have a complete octet, it's going to need one or more multiple bonds to do that. Or if we have a lot of formal charges in our molecule, again, this is a topic that's not going to come up really in this course, but we can improve our Lewis structure by adding some double, triple bonds and so on. But like I said, not important for symmetry purposes. Alright, so we're not going to worry about this last step too much, but I'll show some examples today. Okay, so the best way to review this is just to do a bunch of examples, pick your favorite main group molecule and try to determine its three-dimensional or its Lewis structure, and then we'll see later on how to translate that to a three-dimensional structure. Okay, so the first one we're going to start with is NF3. We need to count the valence electrons first to know how many to use. Alright, so we have a nitrogen and we have 3 fluorines. So we're going to count valence electrons for each of the atoms. Remember that comes from the periodic table, so if we go to our periodic table here, eventually. Alright, we find nitrogen is over here in group 5. These are labeled with Roman numerals, but this is group 5, which means nitrogen has 5 valence electrons. Fluorine is 2 over from that in group 7, which that means each fluorine is going to have 7. So we have 1 nitrogen with 5 valence electrons. We have 3 fluorines, each has 7 valence electrons, an additional 21, and then we have the grand total of 26 electrons. So when we draw this Lewis structure, we're going to make sure that we use a total of 26 electrons. And the way we do that is we start with the central atom, which is nitrogen, the less electronegative. We put single bonds to all the fluorines. The first thing we do is complete the octet of the outer atoms by adding 3 lone pairs to each one, 6 more additional electrons. So now each of these fluorines has its complete octet, 2 from the bond and the 6 non-bonding electrons. After this point, we take a quick count. We've used 24 of our electrons because we have 8 for each fluorine, 3 fluorines, total of 24. We know there's going to be 26 total, so we need to put 1 more onto our central atom here. So that last pair of electrons goes onto the nitrogen as a lone pair. We can take a quick count of formal charge to make sure that we don't need any multiple bonds, or to check if that's the case. So the formal charge for nitrogen, we're going to do this for each atom. So what we start is the number of valence electrons in the neutral atom. As we showed up here, nitrogen has 5 valence electrons as a neutral atom. So that first number is the number of valence electrons in the atom. And then what we're going to subtract is the sum of two parameters for our structure. So we're going to start with, I'll do this in a different color to color code it. The first number we subtract is the number of bonds. So nitrogen has 3 bonds. It has 1 single bond to each fluorine for a total of 3 bonds. And then the other thing we need to subtract is the number of non-bonding electrons. So we include non-bonding electrons individually when they're, so that's the number of lone pair or non-bonding electrons. So nitrogen again has this 2 here. So we do that subtraction and we end up with a formal charge of 0 for nitrogen. We can check it for fluorine as well. Fluorine had 7 valence electrons in the neutral atom as we counted up here. And then each fluorine only has 1 bond, which is bonded to the nitrogen with a single bond. And then we have each fluorine with 6 non-bonding electrons that we put in. 1, 2, 3, 4, 5, 6. And the formal charges on fluorine are also 0. So because we have 0 formal charges, because we have complete octets on each atom, we don't need to draw any multiple bonds. And you probably all knew 5 minutes ago that NF3 is only going to have single bonds, but this is how I sort of verify that. And it won't change the shape or the symmetry of any NF3 whether we had double bonds or not, but we know that we don't need to include them. Alright, let's do one more example, POCl3. So this time we have 3 different types of atoms. So phosphorus, oxygen, and chlorine. Alright, so phosphorus, we go back to the periodic table, also in group 5, right underneath nitrogen. So phosphorus is going to contribute 5. Oxygen is going to contribute 6. It's 1 over in group 6. And then we have 3 chlorines. Chlorine is in group 7. So we have group 5, 6, and 7 elements. So the phosphorus contributes 5 valence electrons. The oxygen, we have 1 of those also, is going to contribute 6. And then we also have 3 chlorines from group 7, another 21. So when we add these all up, we get 32 electrons. That's the number we're going to have to put in here. So we start with our central atom, which is going to be phosphorus. That's going to be the least electronegative atom. We initially have single bonds to each outer atom, oxygen and 3 chlorines. We complete the octet by adding 6 more electrons to each outer atom. Alright, and then if we check how many we've used, we have 4 octets, which is 32 electrons, and that's how many we started with. So we're not going to add any more electrons to this. We don't have any lone pairs on the central atom in this case. But if we look at formal charges this time, we'll see something. For phosphorus, we have 5 valence electrons, 4 bonds, 4 single bonds, no lone pairs. So we have a +1 formal charge on phosphorus. For oxygen, we had 6 valence electrons. This oxygen has 1 bond and 6 valence electrons, so that's a -1 formal charge. And then each chlorine, just like the fluorine from before, is 7 valence electrons, 1 bond, 6 lone pair electrons per 0. But the point is we have a +1 and a -1 formal charge next to each other. Now there's a lot of debate in the field of bonding about how much this actually happens, whether you get what's called a hypervalent phosphorus with 5 bonds. And I don't want to address that debate in this course. It's something we might touch on a little bit later on. But from a general chemistry standpoint, it's very conventional to draw a double bond here. So we have a +1 and a -1 formal charge next to each other. So the way to get rid of those is to make one of these non-bonding pairs of electrons and oxygen into a double bond. So we draw a phosphorus-oxygen double bond. We keep the 2 lone pairs on oxygen. We don't do anything with the chlorines. They already had 0 formal charge. And so this is probably the more conventional way to draw the structure of POCl3, although again there's some real debate in the field about whether you actually get this double bond character or not, or how much of that is really there. So that's a more advanced topic and something we're not going to argue about today. And, well, I'm not with you guys to argue about it anyway, so I guess it's not going to happen. Alright, and then that gives us a quick overview of Lewis structures. That's how we determine the number of bonding and non-bonding electrons. And now we're going to see how we can translate that into a three-dimensional structure using what we call the VSEPR approach. Okay? So VSEPR stands for valence shell electron pair repulsion. And it's a method that's been developed, purely a geometrical method. It doesn't have a lot of basis in actual chemistry, as it turns out. But it's a good way for us to predict three-dimensional shapes of molecules. And that's going to be an important point in this course, because any sort of argument or discussion about symmetry is going to start with a three-dimensional structure. So we need to be able to predict three-dimensional structures. We need to be able to understand what they look like if we're going to start dealing with more advanced topics related to their symmetry, and then how that affects bonding and spectroscopy and all those good things is really the whole flavor of this course, the whole theme of this course. And really what VSEPR is telling us to do, as I said, is primarily a geometric approach, is we're just going to arrange the electron pairs around the central atom, and we're going to try to get those electron pairs as far away from each other as possible. So electrons repel each other, electron-electron repulsion, and so if we put those as far away from each other, we're going to minimize that repulsion. Alright, so the central atom is going to have several bonding pairs that or several pairs of electrons that are bonded to the outer atoms, as well as possibly, as we saw, one or more lone pairs on that central atom. So we're going to arrange electrons around the central atom as far away from each other as possible. That's really the whole idea of VSEPR. Alright, and then there's two parameters that we can determine using VSEPR. Electron group arrangement is the 3D arrangement of all bonding and non-bonding electrons, and there's only really 5 of these that we have to worry about. So when we combine all of those valence electrons, we can define an electron group arrangement around that central atom. Alright, so that's the electron group arrangement, and then the one that's important, again, if we're going to look ahead and start talking about symmetry in the future, is the molecular shape. This is the geometry of the atoms themselves, where we ignore the lone pairs, because when we're talking about molecular symmetry, the lone pairs don't contribute to that. So if we just look at the geometric arrangement of the atoms only, or their geometry, that's going to ignore the lone pairs, and that's going to give us the molecular shape, or the molecular geometry as it's often called. And that's what we need if we're going to start talking about symmetry. So in other words, the lone pairs on the central atom are going to influence the shape of the molecule, but they're not actually going to be used in defining that shape. So some more VSEPR terms that are sometimes helpful, and you may have learned in your previous lives as undergraduate chemistry students. We have what's called the AXE notation. So this is kind of a way of abbreviating all the possible structures for main group molecules, where A is the central atom. And we're going to primarily use this approach for molecules that have one well-defined central atom. If you have larger molecules, then the shape is more complicated, obviously. It's the AXE notation, so X is going to be one of the outer atoms that's bonded to the central atom, and so that's going to tell you how many outer atoms there are. E are going to be any lone pairs that are on the central atom. And then M and N, these little subscripts here, those are going to be coefficients that tell us how many of each we have. Alright, so that allows us to then characterize each molecule in terms of how many outer atoms there are, how many lone pairs there are, and each of those possible combinations of M and N is going to define the molecular geometry. The steric number is going to be the sum of M and N, and that's going to give us the total number of valence electron groups, I should say. We would typically think of electrons as being in pairs in these, obviously. So we're going to have the total number of electron groups around the central atom. And it's this parameter here that defines the electron group arrangement. So if you know the total number of electron groups, the number of bounded outer atoms, and the number of lone pairs, that's going to define the electron group arrangement. One thing I didn't quite emphasize enough is that when we're doing AXE notation, we're counting pairs of electrons. We're not counting each electron individually anymore. And again, that's because, as we all know, each orbital can accommodate 2 electrons. So when we're talking about groups of electrons, we're going to typically think of them as being pairs of electrons that are arranged around the central atom. And then another important parameter for VSEPR is bond angle, and it's important to at least have a qualitative appreciation of this when we talk about symmetry, whether it's linear or bent, for example. But it's precisely defined as the angle between 2 outer atoms. So if we are AXN inside the structure, we're going to have more than one outer atom. If we would define the angle between them, this will erase eventually. And we're going to use the central atom as sort of the vertex of that angle. So as an example, if we have some AX structure, we can define the angle between the 2 X's. We can abbreviate that as with a little angle sign, XAX, which those are the 3 atoms involved. So a bond angle is always defined by 3 consecutive atoms in a structure, whether we're talking about these simpler AXE structures or something more complicated that we might get to later in the course. Bond angle is just that definition for anything. Alright, so that gives us some terminology. Now let's start doing VSEPR in a little bit more real detail. Alright, so as I said, we're going to have different combinations of bonded and non-bonded electron pairs around the central atom, which gives us different steric numbers. So we're going to go 1 through 6. Steric number of 1 is very trivial, so we're going to first start by defining the electron group arrangements. This is really any combination of X and E that add up to this number. We're going to start by just giving you the structures where all of them are outer atoms. But anyway, if we have just one thing bonded to the central atom, of course it's going to be linear. So this is the trivial case, because if you have two atoms, they can't be anything but linear. That's just geometry. If we have a steric number of 2, the electron groups are going to arrange themselves in a linear fashion. Alright, so if we have an AX2, let's say both of them are X's, those also, if we want those pairs of electrons to be as far away from each other as possible. If you have 2 of them around the central atom, the farthest away from each other they can be is 180 degrees. So the bond angle would be 180 degrees for anything that has a steric number of 2, the angle between the pairs of electrons. Steric number of 3 is going to have the electron group arrangement called trigonal planar. So it's just a flat triangle. In this case, again, putting everything as far away from each other as possible. The way we can do that with 3 electron groups is to put them in a triangle 120 degrees apart. So all of the bond angles are 120 degrees, are exactly identical. And so that's trigonal planar, steric number of 3. We're going to go on to 4, 5, and 6. Those are the highest ones we'll do. So a steric number of 4, this is the first one that we have to start thinking three-dimensionally. And as you're all probably aware, this is the tetrahedral electron group arrangement when we have 4 things around the central atom. We can draw that sort of like this, where the wedge means it's going out of the page, the dash means it's going into the page. And again, this is a three-dimensional structure. The bond angles for this are not as intuitive as the rest. They're that magic number, 109.5. So unless you're an expert in three-dimensional geometry, that's not something you can easily rationalize, but that's the number we would see for a tetrahedral electron group arrangement. Steric number of 5 is the weird one in some ways. So we call it trigonal bipyramidal. It's not a terribly complicated shape, but it does have 2 different bond angles, unlike the rest. So if we want to draw trigonal bipyramidal, what we have is a trigonal plane. So that's 3 of the x's, and the other 2 are going to bisect that plane at a 90-degree angle. And so what we have in this, if we look at adjacent x atoms, the ones that, the 2 smallest bond angles that are possible, we have this angle here is going to be 90 degrees. The angle between any of the apical positions and one in the trigonal plane is going to be 90. But then we also have within the trigonal plane itself 120 degree angles. So we have 2 different bond angles in this structure, 90 and 120. That's why it's a little bit strange compared to the rest. And then finally, the highest that we'll go to, and this is a very important geometry also for transition metal compounds, is octahedral. So as I said, this course is going to focus primarily on transition metal compounds, and really there are transition metal compounds that also have all of these geometries, and perhaps even some more complicated ones that we might get into. So these are also important for stuff we'll do later in the course, to at least be able to understand the geometries. They're not predicted in the same way using transition metals, but they are the same types of shapes. So octahedral can be thought of as a square plane, so we have 4 x's arranged in a square, and then again 2 apical positions that would go into and out of that square plane. But we still have only one, in this case, only one bond angle of 90 degrees. Every atom is 90 degrees from the next closest one to it. So those are the only bond angles we have for an octahedral case. So those 6 basic arrangements are the electron group arrangements. But as we saw many times, especially in main group chemistry, our central atom is going to have some lone pairs associated with it, which then are going to give us different molecular geometries. So what I should point out is that these electron group arrangements, if you don't have any lone pairs on the central atom, the electron group arrangement and the molecular shape or molecular geometry are identical. So an AX6 molecule would be an octahedral electron group arrangement and an octahedral geometry. But if you have lone pairs, the electron group arrangements are going to be defined by the total number of electron groups, but then we're going to have a different name for the geometry. So the first one we'll start with, the simplest one, is AXE. It's a steric number of 2, so that gives us a linear arrangement of the 2 electron pairs, but one of them in this case is a bond atom, one of them is a lone pair. This one again is trivial because we only have 2 things. We have an A and an X. Remember that the molecular shape is going to only concern itself with the atoms themselves, not the lone pairs. So it's just an A and an X bonded to each other, so you have a linear geometry, pretty straightforward. But if we go to AX2E, there's a total of 3 electron groups, 2 X's and 1 E's, so they're going to be trigonal planar. One of those is a lone pair. It doesn't matter where it goes because all the positions are equivalent. And now we have 3 things, but they're not linear anymore. They're in a bent angle, so we call that a bent geometry. And the bond angle is still pretty close to 120 degrees, but not exactly because of the lone pair. We have some molecules are AXE2, not as common, but we can have that as well. And so AXE2, still 3 total electron groups. This time 2 of them are lone pairs. All of the positions are equivalent, so it doesn't really matter where we put those. 2 things bonded to each other has to be linear. So if it's AX with any number of lone pairs, if it's just one X, it's going to be linear, of course. If we go on to steric numbers of 4, AX3E, now we're talking about 4 total electron groups. Those are going to be tetrahedral. And just like trigonal planar, all of the tetrahedral positions are equivalent. They're all 109.5 degrees apart from each other. And so we can put the first lone pair wherever we want. The easiest way to see this geometry is to put it on that top position. And then we call this trigonal pyramidal, or sometimes just pyramidal. So this is a molecular shape that's derived from tetrahedral, but we have a lone pair in one of the positions. And so the remaining atoms define what's called a trigonal pyramid. If we go to a bent, sorry, I gave this one away. AX2E2 is going to be another bent geometry. So in this case, we have still 4 total electron groups. 2 of them are lone pairs. All the lone pair positions are equivalent in a tetrahedral arrangement. And again, we have very clearly not a 180 degree bond angle, but closer to 109.5, so we also call this bent. So there are 2 bent geometries, AX2E, AX2E2. Qualitatively, they're both the same, but you would expect them to have different bond angles. Okay, moving on to higher electron group arrangements. This seems to be the one that people mess up the most. So AX4E is a total of 5 electron groups, so they're going to be trigonal bipyramidal to start with. That's the electron group arrangement. And now we have to decide where the lone pair goes. So trigonal bipyramidal, as I said, is a strange one where there's 2 different positions. These top and bottom positions have 90 degree bond angles. The positions that are in the triangle have 90 and 120 degrees. For the lone pairs that we're going to put in here, we want the lone pairs to be as far away from everything as possible. Lone pairs repel more strongly than bonding pairs. So it turns out that it's better to put the lone pair onto these equatorial positions. So anytime we have lone pairs with a steric number of 5, all of the lone pairs are going to go onto the triangular plane, and we're going to put X's in the rest of them. Now this is kind of a weird geometry, not particularly common in transition metal chemistry, but we call this a seesaw geometry. And if we turn this over on its side, you can see that. And I also encourage you to, if you have 3-dimensional models, you'll occasionally need to use those in this course, or sometimes it's very helpful for visualizing things. So you could build some of these models. I have some models in my office if you want to come see them. You don't have your own set. And we can see these shapes a lot better in 3 dimensions. But we have AX4E is what we call a seesaw. We have 2 other geometries that involve 5 total electron groups. So AX3E2, still 5 total electron groups. So we have a trigonal bipyramidal arrangement of those groups. I'm not doing a very good job of drawing these sometimes. Alright, so we start out with that. We have 2 lone pairs this time. And again, as I said, lone pairs are going to go always on the triangular plane. The other 2 positions, or the 3 positions, are going to be the outer atom X, and we call this T-shaped. This one is fairly obvious, T-shaped molecule, like that. Okay, so we call that T-shaped. AX2E3, you see this with some compounds of xenon. 5 total electron groups. 3 lone pairs. They all go on the triangular plane this time. All 3 of those positions are now lone pairs. X is on the top and bottom, and this one is very clearly linear. So if it's AX2 with 2 outer atoms and however many lone pairs you have, the only 2 choices are linear and bent. This is one that goes linear. And then finally we have 2 geometries that involve 6 electron groups that are going to be important for us. These ones do occur quite commonly in transition metal compounds as well. And so we have AX5E, 6 total electron groups. They're going to be octahedral. In an octahedral geometry, all of the positions are equivalent, so the lone pair can go wherever we want it to. This geometry is best visualized by putting this on the bottom, but all the positions are 90 degrees apart from each other, so it doesn't matter where you put the lone pair. And this is what we call square pyramidal. So it's also a pyramidal geometry, but with a square base instead of a triangular base, so we call it square pyramidal. And then finally, if we have AX4E2, another common geometry that occurs in transition metal compounds, although not typically with 2 lone pairs in the central atom, but still the shape is one we'll see. AX4E2 is 6 total electron groups, so we have an octahedral arrangement. This time we have 2 lone pairs. The lone pairs want to be as far away from each other as possible, so we put those on opposite sides, and then the rest of the positions get filled in with the atoms. And so this one is square planar. Professor that I had in graduate school always hated the name square planar because squares are always plane, so he just likes to call it square. But at any rate, it's a square planar geometry where the 4 atoms arrange themselves in a flat square arrangement, and the 2 lone pairs are above and below. But square planar is also a shape that we'll see a lot in transition metal compounds. All right, so that takes us through a really fast overview of VSEPR. So if you need to review that, please do that on your own. And also I have this website here. As far as I know, this is still active. It's a very good way to visualize these things in 3 dimensions and help you learn some of these geometries a little bit better if you need to review them. So I have that down there for you to check out on your own if you feel so inclined. Alright, so let's do a few examples of using VSEPR to determine the geometry of a molecule. Alright, so we'll start with PCl5. And for VSEPR, we do need a good Lewis structure, or at least a reasonably good Lewis structure that at least has the correct number of bonding and non-bonding pairs on the central atom. And so we're going to start by counting electrons. We saw phosphorus before is in group 5. So it's going to contribute 5 valence electrons. Chlorine, we have 5 of them in this case. 5 chlorines, and then each chlorine was, as we saw before, is in group 7, so there's going to be 7 valence electrons from chlorine. This gives us another 35. So this one has 40 valence electrons, and so when we arrange things around the central atom, all 5 chlorines, we complete their octets first. I can't think of an example where you wouldn't have a complete octet on the outer atom, unless it's hydrogen, of course, which doesn't get lone pairs. But we do that for chlorine. At this point, we've used all 40 electrons. So we have 5 octets. That's a total of 40 electrons. That's how many our molecule has. So our central atom doesn't get any lone pairs. We could start thinking about double bonds, although there are none in this molecule, but that's not really important for VSEPR. We just need to know if there's any lone pairs in the central atom. So this is a fine place for us to start, and what we see is that this is going to be categorized as AX5. We have a central atom, we have 5 atoms surrounding that, we have no lone pairs on the central atom. For AXE notation, you only count lone pairs that are on the central atom. And so this is a trigonal bipyramidal electron group arrangement and a trigonal bipyramidal geometry because there are no lone pairs. And so if we want to draw this in relatively accurate 3 dimensions, it would look like this. Okay, so that's trigonal bipyramidal. Yeah, let's do one more, sulfite, SO3 2-. So I'm not going to go through all the steps to draw the Lewis structure because I think we're probably beating a dead horse at this point. But for SO3 2-, what we get is a Lewis structure that would look like this. We have to add in 2 extra valence electrons for the -2 charge, but when we do all that and arrange the electrons around the central atom, this is what we would get. Now we can stop here. We have a complete octet in our central atom. We know how many lone pairs and everything there are, so we don't have to really worry about multiple bonding, but there is going to be one double bond in the structure if we're looking at the best one. So the best Lewis structure for this is going to have 1 sulfur-oxygen double bond. And then what we probably recognize, another topic from undergraduate chemistry that's really not important for this course, but we should, if we want to be complete, mention it at least. We have what's called resonance. So we have this, this best structure here that's going to have 1 sulfur-oxygen double bond. That minimizes formal charges, but then we have really 3 equivalent structures that all would have 1 sulfur-oxygen double bond. So we can put the sulfur-oxygen double bond on the other side. Where we're just moving around those pi bonding electrons. Or we can put it, as I've drawn it, in the top position. A little bit running out of space here, so I apologize for the mess. You guys will get used to my awful handwriting. It's only a matter of time. Okay, so we have these 3 resonance structures, but they're all, whichever one we use, or even if we don't draw the resonance structures, we can still predict the geometry quite easily. So we have 3 outer atoms, so it's going to be AX3. We have 1 lone pair on the central atom. That doesn't change in the resonance structures. Those are all that's all there. The sulfur-oxygen pi bonding electrons that are moving around. So we have AX3E, and as we'll recognize, that's a trigonal pyramidal arrangement. So building the structure systematically, we have a sulfur, we have 4 electron groups. They're going to be tetrahedral. One of those is a lone pair. I'm going to draw it like that in this case. The other 3 are oxygen. We have delocalized pi bonds, which makes this a little bit tricky to draw. But nevertheless, it's going to be a trigonal pyramidal geometry for these 3 resonance structures. Alright, so that takes us to the end of VSEPR, at least the topic that the amount that I'm going to cover in this course. Please do review it. It won't be a point of emphasis, but if I expect you to say something about the symmetry of a molecule, you do need to know the shape of the molecule. And this is often how we do that. Now, the last thing we're going to talk about today, very briefly, and we'll get into some more details of this next time, are coordination compounds. And these are going to be the ones that are really the ones that we feature in this course. Main group chemistry is something we'll talk about a little bit, but most of our efforts, especially when it gets time to talk about symmetry and bonding and spectroscopy and all the stuff that are the major themes in this course, is going to deal with coordination compounds. So a coordination compound, broadly defined, it consists of a metal. All right, so as this being an organic chemistry course, transition metals are our favorite. So a compound consisting of, you can have more than one metal, of course. There are certain types of coordination compounds that are multimetallic. And it has one, or in most cases, usually more than one. And these things that we call ligands are small groups of atoms, typically small groups anyway, that donate electrons and bond to the metal. Alright, we're going to leave the bonding in these things purposely vague for now and talk about it in a lot more detail in this course. We just want to understand what coordination compounds are and some basic features of them. Alright, so coordination compounds, metal and 1 or more ligands. And so we have typical structures for coordination compounds are, for most transition metals, you're going to see octahedral as a very common arrangement. As I mentioned earlier, there are coordination compounds that have pretty much any geometry you can think of. And for a long time especially, it was a very hot area of research to try to design coordination compounds that had increasingly strange and increasingly unheard of geometries, and So, really if you go through the literature, you can find almost any example. But a lot of the classic coordination compounds, the ones that really got this field started, as well as a lot of compounds that are still of importance today and things that we'll talk about in this course, are octahedral. So you have your metal, and if we're just abbreviating it in very general terms, we have our 6 ligands that are arranged in octahedral fashion around the metal. We'll start talking next time about different types of ligands you can have, and that's going to be an important thing that comes back when we talk about bonding, or that there are different categories of ligands, but in many cases the 6 ligands arrange themselves in an octahedral fashion around the metal. You can sometimes have compounds that have mixtures of different ligands, so these L's don't necessarily all have to be the same. You can have what are called homoleptic compounds where they are all the same, or you can have heteroleptic compounds where one or more of these ligands is something different than the rest. So there's a lot of possibilities, but octahedral is the geometry that is certainly most common. Another one that we very frequently see, especially for D8 metals, so we're going to talk next time about how to count D electrons. So if that doesn't make any sense, then just hold your breath until next time. But when we know how many D electrons there are on the transition metal, we can use that to sometimes help us predict the geometry. So in many cases, and especially for the second and third row transition metals, D8 metals are going to be usually square planar. For reasons that will make more sense when we start talking about bonding in these compounds. There are some exceptions with nickel 2. So nickel 2 is a D8 transition metal ion. We'll talk about oxidation state and electron counting next time, so hang tight. But anyway, if you have a nickel 2 compound, nickel with a formal +2 oxidation state or +2 charge, sometimes those are tetrahedral or octahedral. Tetrahedral is another common geometry for transition metal compounds that we'll see quite a bit as well. And so square planar is just a metal with 4 ligands around it, and when you're going to those D8 compounds especially, you're going to see this a lot. Alright, so platinum and palladium are the ones that come to mind. And then finally we can have metals that are formally D10, and these are the ones that are the total wild card. These ones are very unpredictable. Again, reasons that will make sense later on. But essentially when you have a D10 transition metal, it doesn't have a preferred geometry. The preferred geometry is going to be determined by things a lot more related to the ligands in some cases, or sometimes to the nature of the specific metal ion you're talking about. So D10 metals have very unpredictable structures and are in some sense what you would say very promiscuous, in that they can adopt a number of different coordination geometries. But there is one example of a D10 transition metal that has usually a pretty predictable geometry, and that's gold 1. So gold +1 has 10 D electrons, and this is almost always linear. And I don't think we'll talk about relativistic effects in this course, but if you've heard that buzzword before, the linear geometry of gold is because of relativistic effects at the transition metal center. And for various reasons that leads to the preferred arrangement being linear. So if you have, for example, this ion, gold with 2 chlorines, 2 chlorides, with a -1 charge, gold 1, this is going to be a pretty classical linear gold compound. You can also have neutral gold compounds where you have gold chloride with something else on the other side, 2 different ligands that are in total no net charge. This is also almost always linear. So you get a lot of linear 2-coordinate compounds with gold. From a symmetry standpoint, those aren't very interesting for us, so we're not going to really deal with those, but we should be aware of that from a coordination chemistry standpoint. Alright, that takes us to the end of what we wanted to cover today. Since I wasn't in class with you guys, I probably went faster than I normally would on this, but just to give you a brief overview and at least make you feel like you're not totally missing out of this course during the first day when I'm away. So I will be back for the lecture on Thursday, and in that time we'll go over some more inorganic chemistry topics that are important for us to remember for this course. And during those in-person lectures, I definitely encourage you to ask questions as we go along, and if you have any questions about what I talked about today, you are welcome to bring those up during class on Thursday, and I'll give you an opportunity to do that. But anyway, we'll try to keep moving forward through the review stuff as quickly as possible, because we want to get into the more interesting materials that we have in this course. All right, so thank you for tuning in, and I will see you guys in class on Thursday.